Welcome to this TMDL presentation for Big Hollow Lake. My name is Jim Hallmark, and I'm an environmental engineer with the Iowa Department of Natural Resources, and I will be presenting the findings of our water quality improvement plan for Big Hollow Lake. Before we get started, I want to make you aware that there is language assistance available if you are non-English speaking or English is not your first language. If you need help, please call the number listed on this slide, 515-725-8200. This presentation has been prepared and is being presented as part of the public review process for the Big Hollow Lake Water Quality Improvement Plan. This presentation was originally posted for a 30-day public comment period beginning on May 1st of 2025. However, during the final EPA review process, corrections were made in the document which required reopening the Water Quality Improvement Plan to a new public comment period. The current public comment period will go through September 8th of 2025. If you have any comments or questions about this presentation and the Water Quality Improvement Plan, you can submit those comments to the individuals at their respective emails listed on this slide. Those comments must be received by the end of the public review comment period, which is September 8th of 2025. Also, if you would like a copy of the Water Quality Improvement Plan, a link to that document will be provided below this screen. Just a couple of housekeeping items related to terminology. Impairment is a word that we frequently use. An impairment is defined as a weakened state or condition or diminished in function. When we're talking about a water body being impaired, there is something preventing it from meeting its designated function or expectations as outlined in the water quality standards. The other two terms are TMDL, or total maximum daily load, and water quality improvement plan. These are two different terms and have different meanings. However, they are sometimes used interchangeably. So what is a water quality improvement plan? In short, a water quality improvement plan is a written document or report that includes the development of the TMDL, or total maximum daily load, along with other information such as an implementation plan. So the Water Quality Improvement Plan is the actual document that outlines or identifies our TMDL. So what is a TMDL? As defined by the EPA, TMDL, or total maximum daily load, identifies the maximum amount of a pollutant that a water body can assimilate and still meet water quality standards. In other words, it meets its intended function or purpose and has no diminished capacity. Here's a picture to help illustrate what a TMDL is. This is a picture of a mule harnessed to a cart. This is the system, the mule cart system. Under normal circumstances, the cart would be loaded with boxes and products and other materials, and the mule would pull it around through the village to its various destinations, and it would function as expected or intended. However, as shown in this picture, there comes a point in which the load placed on the cart results in an imbalance in the system, causing the mule to be lifted off the ground. In this instance, the system is impaired. It no longer functions as expected. This is certainly a case of diminished function, but all is not lost. The load on the cart can be redistributed, resulting in the mule's feet resting on the ground again and the system being restored to function as expected. We can compare this mule cart system to our lake or aquatic system. The mule and the cart represent our lake system, and the load or boxes on the cart represent a pollutant load. Just as with the mule cart system, our aquatic system can handle a certain amount of load or boxes and still function as expected. However, there comes a point when the pollutant load reaches a tipping point, resulting in the aquatic system not functioning as expected. There is too much pollution or load on the system, resulting in diminished function. Again, all is not lost. The pollutant load to the aquatic system can be reduced, allowing it to function as expected. Here is an outline of what I intend to discuss for the remainder of this presentation. We want to present and discuss in more detail what is in the Water Quality Improvement Plan. Included is that in that will be a description of Big Hollow Lake and its watershed, a discussion on water quality assessment, how we went about monitoring and assessing a water body to determine if it is or it is not impaired. We will discuss TMDL development, which includes looking at potential pollutant sources and how we go about calculating our final TMDL number. Then we'll have a brief generic discussion on implementation planning. Things involved in that are local involvement, where we want, and here we want to discuss implementation of strategies or practices, including best management practices, and continued monitoring of the water body. And last of all, as part of the Water Quality Improvement Plan, we have a public review and comment period. And this includes a public meeting where we present the findings of the study. And this presentation acts as a virtual public meeting. Big Hollow Lake is located in southeast Iowa in Des Moines County, approximately 5 miles southwest of Minneapolis. The lake is located within the 798-acre Big Hollow Recreation Area, which is owned and operated by the Des Moines County Conservation Board. And that recreation area is highlighted here in this green and outlined down here in the far lower end of the watershed. Big Hollow Lake has a watershed of approximately 4,700 acres, which is outlined here in blue. The watershed has a 27-to-1 lake ratio, which means there's 27 acres. For every 27 acres of watershed, there is 1 acre of lake surface area. This is a bathymetric map. It is a map of the lake bottom contours. The numbers are small in this slide, but looking down here at this end, which is close to the dam and the spillway, it's much deeper with contours showing up 28, 36, and 40 feet, while up here at the upper reaches, definitely much shallower with contours of 8, 12, and 16 feet. So obviously, as we get closer to the dam and the spillway, it's much deeper. This particular map is commonly used by those who fish to help them identify deep spots in the lake and potentially fishing hotspots. The surface area of Big Hollow Lake is approximately 169 acres. And an acre is approximately the size of a football field as measured from goal line to goal line. And we also have a volume of Big Hollow Lake of approximately 2,700 acre feet. And an acre foot is would be like 1 acre of land with 1 foot of water over it. And an acre, as mentioned before, is approximately the same size as a football field. So the volume of Big Hollow Lake, 2,700 acre feet, would be like 2,700 football fields with 1 acre of water over the top. We also look at land use within the watershed. And from this map here, we can see that row crop is the predominant land use within the watershed. It makes up approximately 70% of the land use within the watershed. And the next closest to that is a forested area down here in this green, which makes up 11% of the watershed. And then other uses make up the remaining amount, roughly 20%. We also look at slope distribution. We can see here that 74% of this watershed has a slope of 5%, and 53% has a slope of less than 2%. Overall, this is a fairly flat slope with the exception of the gullies adjacent to the gullies and the streams, and particularly down here in the gullies where we can see those bright reds and oranges. Slope is critical when we're talking about erosion to offer some perspective when traveling in mountainous regions where the terrain is steep. You'll see warning signs posted at maybe 4, maybe 5%. So when traveling down these grades in a car, you begin to pick up speed and energy very quickly, unless there is some type of energy dissipation, such as a brake. Same thing happens in our watersheds. When we have steep slopes, the overland flow from the runoff goes downhill and it begins to pick up energy. And as it does, it picks up and carries soil particles, the sediment, with it, unless there's some way of dissipating that energy and slowing it down just like we would in our car by applying the brake. So unless there is some way to slow it down, it just carries that sediment on downstream. So an assessment of Big Hollow Lake. So what's wrong with Big Hollow Lake? Well, it's impaired for algae, pH, and turbidity, which results from excess nutrients in the lake, specifically phosphorus and nitrogen. So how do we go about doing this assessment? First, we do data collection. We're going to collect water samples and send them to the lab for analysis. This particular slide shows the sampling location for Big Hollow Lake, highlighted by this disc. The sampling point is typically at the deepest part of the lake, near the spillway. Samples are collected from the same spot from year to year, and samples are collected during the recreation season, which is from March 15th to November 15th. However, a majority of the samples are collected between Memorial Day and Labor Day. A DNR employee gets in a boat and goes out to the sampling point. They collect the samples and send those to the lab. The lab does the analysis to determine the chemical and physical composition and makeup of those samples. Looking for phosphorus, nitrogen, chlorophyll, which is an indicator of algae, dissolved oxygen, and E. coli. Another important monitoring and sampling parameter used in the assessment is determining water clarity or turbidity. If we look at a lake, the lake might appear to have a green tint or too green, which would indicate an algae in the lake, or we might see it brownish or reddish, which would be an indication of sediment, sediment causing the turbidity in the water. And the way we measure this is a quick device. It's called a Secchi disc. A Secchi disc is a circular disc. It's about 30 30 centimeters in diameter or 12 inches, and it's painted black and white in alternating quadrants. This Secchi disc is attached to a tape measure, which is lowered into the water until it is no longer visible. At that point in time, the measurement is taken and recorded. So for Big Hollow Lake, the average Secchi depth is 1.4 meters or 4.5 feet. So you have 4.5 feet of visibility within the lake. All right, also, once the data is collected and analyzed, we plot it on a graph. This particular graph, we're going to plot it by year on the x-axis and by the TSI values or a trophic state index on the y-axis. The trophic state index or TSI is a classification system which is designed to rate a water body's amount of biological activity. So the higher the Secchi depth or chlorophyll values are, would suggest a higher amount of biological activity, typically algae, and the lower a TSI value is, it would suggest a lower amount of biological activity, so less algae. Also, I have plotted two lines, a red one and a blue one. The red line indicates our impairment limit. So as we measure our Secchi, our chlorophyll and our Secchi depths, we would hope and want those TSI values to be less than 65. If they exceed the value of 65, then the water body is placed on the impaired waters list. Now this 63 is significant because once the water body is on the impaired waters list, in order to remove it, these TSI values must be below the value of 63. So once it's impaired, we want to clean it up. We need those TSI values less than 63. So we plot our data. These are mean or average annual values. We can look at this and see that for these green triangles, which is our chlorophyll, typically and consistently above the value of that 65 threshold, particularly in the later years. Not so much so in the earlier years, but in the later years, our chlorophyll values are typically above 65. Also, we can look at the blue diamonds, which represents our TSI Secchi depth values, and those two are consistently above the 65 threshold. So for Big Hollow Lake, then we have it being impaired for both algae and turbidity. In addition to the algae and turbidity impairment, Big Hollow Lake is also impaired for pH. We want our pH values to fall between 6.5 and 9, and anything outside those values indicates an impairment. So we can see early on at Big Hollow Lake, we had consistently values above 9, and as far as late as 2019, we had values above 2019. And since then, we haven't had any, so we obviously see a good trend, a positive trend in the pH values, and hopefully that trend continues. All right, so this is a slide that you've seen before. What is a TMDL? Again, it is the maximum amount of a pollutant that a body of water can assimilate and still meet water quality standards. So when we talk about TMDL, we look at four different categories or four areas of interest. One is the target. What is our target pollutant? What are we trying to reduce or eliminate from the system? The second is our sources. Uh, what are the potential or possible pollutant sources? Where does the pollutant come from? Thirdly is allocation. Is how is the pollutant allocated amongst the different sources? And fourth is the equation. This is the math part of it. How do we how we go about calculating and determining that total maximum daily load, and how we allocate that TMDL throughout the watershed. Okay, so as mentioned, our first one is our target. In this case, we're trying to minimize phosphorus. Phosphorus is a nutrient needed for aquatic plant growth, and too much of it leads to algal growth, algal blooms. Algal growth can lead to pH spikes. So during photosynthesis, algae consume carbon dioxide, which leads to a decrease in carbon dioxide and an increase in pH. Another concern is turbidity or water clarity. High turbidity or low water clarity results from algal blooms, or it could result from a high sediment content in the water. And that sediment is typically laden with phosphorus. And that's why we want to eliminate sediment and phosphorus getting to the lake. Remember, earlier we talked about the water either having a green tint or brownish or reddish tint. Well, that's because of the sediment in the water, or if it's got a green tint, it's generally going to be caused by an algal bloom. And the third thing here is how is phosphorus is transported by surface runoff and groundwater flow, either in a dissolved or a particulate form. So our objective is to reduce the sediment runoff in the watershed, reaching our water body of interest. And reducing the amount of phosphorus will reduce algae and help to stabilize changes in our pH, as well as reducing the turbidity concerns. Okay, the next thing was our sources. Where does that pollutant come from? Well, we have two target sources, or sources that are divided into two categories. We have our point sources and our non-point sources. The point sources are those sources that require a discharge permit. A good example of a point source would be a wastewater treatment plant or a combined sewer or a very large storm sewer. And some of the larger communities have these, what's called an MS4 community, and they need a permit to discharge as well. The discharge permit has a limit on the amount of pollutant that the permittee can discharge in the effluent. These point sources can also be referred to as a waste load allocation. And within the Big Hollow Lake watershed, there is one point source located within its borders that is permitted to discharge phosphorus. Our second potential source would be our non-point sources. Those are the sources that do not require a permit. Those things could be storm runoff, a deposition of manure in streams, grazing animals, wildlife, urban runoff, failing septic tanks, or even stream bank erosion. All those things can contribute to the phosphorus in the watershed. And those are the non-point sources. Okay, so here we have a pie chart. that shows how our total phosphorus, our existing total phosphorus, is currently allocated within the watershed right now. And we can see from this pie chart that 60% of our total phosphorus comes from row crops, which is not surprising considering that 70% of the land is in row crop. The next highest source is come from an internal loading, which is approximately 20% of the total load. Now, an internal loading is phosphorus that exists within the system already. It could, it's suspended in the water, or it's settled to the bottom along with settled sediment. That bottom material from the lake can be stirred up by fish, or sometimes, during change in seasons where the cold water falls to the bottom and the warm water rises, that can cause some turbulence. And even in shallower waters, wind action can stir up that bottom sediment, again, making that phosphorus available for uptake by aquatic plants such as algae. And the remaining 20% comes from various land uses, urban or grassland, a CRP, pasture. I didn't specifically mention the point source on this particular slide because it's 100 pounds per year. Basically, it's only 1% of the total load coming from that point source. So pretty insignificant compared to the overall loading. And so through our analysis, we've determined that the total phosphorus currently reaching Big Hollow Lake is approximately 7,400 pounds. Again, through analysis, we've determined that the existing load is 7,400 pounds, and our TMDL is approximately 2,200 pounds, meaning that we need to reduce the existing load by 5,200 pounds, or a 70 to 71% reduction. Okay, so this is our TMDL equation. Our TMDL is equal to the summation of our waste load allocation. Remember we talked about that real briefly, that the waste load allocation is equivalent to all of our point sources, those permitted sources. Our load allocation, and here's a summation of all of our load allocations, and that is our non-point sources, those sources that do not require a permit. And then the last part of the equation is our MOS, or margin of safety, which we apply to take into account uncertainty or unforeseen sources that we didn't account for or take into effect. So again, here's our TMDL equation. We have, through analysis, determined that the TMDL, the total maximum daily load that the lake can assimilate and still meet water quality standards, is 2,200 pounds per year. All right, so we know that our waste load allocation, our point source, discharges approximately 100 pounds of phosphorus per year. And our margin of safety is 10% of this value. And remember, that margin of safety is to account for uncertainties in the system, and that's 219 pounds per year. So taking what we know, the 100 and the 219, and subtracting it from this value, leaves us with approximately 1,900 pounds of phosphorus per year to be allocated towards our load allocations, which again are those non-point sources that do not require a permit. And just presenting it in a different fashion here. Again, this is our existing load of phosphorus, annual phosphorus load. This is our target load of our TMDL, meaning we need to reduce this value by 70 to 71%. And this is how our TMDL, or our target load, is being allocated, with 100 towards our point sources, roughly 1900 towards our non-point sources, and then setting aside 219 for our margin of safety. The last thing we want to talk about real briefly is an implementation plan. We provide some general discussion regarding some possible BMPs that can be put into place. So, and also where we certainly, as part of the implementation plan, is to encourage local participation, and it also includes future monitoring to measure the effectiveness of any strategies or practices put into place. So as a note, a watershed management plan for Big Hollow Lake has been developed, and it includes a 20-year plan for implementing some of the BMPs we will discuss. There are 3 different categories of best management practices. The first one is land management, which is prevention, where we prevent the pollutant of concern from leaving the site or its point of origin. We want to keep it confined, keep it contained at its source. This particular practice can also be beneficial to soil and water quality. Next is a structural or mitigation. Treating it along its path. What happens when the pollutant leaves its source of origin? How do we address it then? And how do we prevent it from going further downstream? So we want to trap it or intercept it. And the last one is in-lake remediation, treating it after the fact. Once it's in the lake, what can we do? So some of our land management or prevention practices, these are all best management practices. We have conservation till or no-till, cover crops, perennial streams, and manure management plan. And these are just some of the practices, certainly not an inclusive list. Here's one method of land management is through no-till farming. This is a way of planting and growing crops without disturbing the soil through tillage. By not disturbing the soil, the soil stays in a tight matrix, which reduces erosion, and also by leaving crop residue from last year helps prevent soil erosion and improves soil health, and increases by increasing organic matter. And the second one was our structural mitigation. What happens when it leaves the pollutant? Remember, in this case, it's phosphorus. What happens when that pollutant leaves its source? Well, here's some examples. Buffer strips along the edge of creek stream banks, sedimentation basins or wetlands. Here's a sedimentation basin. Remember when we were talking about slopes, how when we have steep slopes, the water picks up energy, and as it picks up energy, it picks up those sediment, and we need a way of slowing it down or stopping it. So as that water comes down, it hits this basin and distributes or dissipates the energy so that sediment can settle out, and then decanted water flows over the weir and on downstream, leaving sediments deposited in this basin. As part of the Big Hollow Lake Watershed Management Plan, 2 sedimentation basins were constructed in 2024 on the west side of the lake near the campgrounds in areas of high erosion. And our last one is in lake remediation, fisheries management, trying to control those rough fish that stir up sediment from the bottom, some shoreline stabilization and targeted dredging. And here's a picture of targeted dredging where the lake is lowered and heavy equipment is brought in, and that sediment from the bottom is removed and disposed of. One of the issues with this is it's probably fairly expensive to do. Okay, so what are the next steps? Well, obviously we want to continue monitoring to measure the effectiveness of any strategies or practices that have been implemented. And obviously we always want to encourage locally led efforts where we can promote some awareness, of what's going on in the watershed, create a watershed group, develop a watershed management plan, which they have already done for Big Hollow Lake. And they've also, like I had mentioned in an earlier slide, implemented some water quality improvement plans. So even after all this, and then the DNR would make itself available for assistance as needed. This brings us to the end of our presentation. As a reminder, we are in a public review comment period that ends on September 8th of 2025. If you have any comments or questions related to this water quality improvement plan, you can submit those comments and questions to the individuals at their respective emails listed on this slide. Again, those comments must be received by September 8th of 2025. And again, thank you for watching.